Alright, so let's continue further. Now look at problem 13. And this one states if the curve below is rotated about the x-axis, the resulting solid looks like an infinite decreasing string of beads. And where the curve is y equals e to the negative x divided by 10 times it by sine of x for x is greater than or equal to 0. And in part A of the question we're asked, find the exact volume of the nth bead. Yeah, so when we rotate it about the x-axis, we get a string of beads, so the nth one, we want to find the volume. And then it says, we're given a hint, use either a table of integrals or a computer algebra system. And yeah, this is the calculus book is a bit old. They could just use an online calculator instead, because there's a lot of powerful ones out there. So, and then part B says, find the total volume of the beads. Alright, so let's jump right into the solution. So let's look at solution to A first. And this says, first let's graph it out first. So this is the curve y equals e to the negative x over 10 times sine x. So here's the curve, and I'm using Desmos calculator. If you graph it out, it looks like this. It's just just squiggly line. That's decreasing. And if you rotate about the x-axis, so this is the x-axis, rotate it all the way across, you're going to get something that looks like this in 3D. Yeah, so you have a bunch of beads in 3D. It's a bit hard to visualize like that. Yeah, and then, yeah, so if you graph it out and rotate it, you have a bunch of beads. And in fact, so the solution manual didn't graph it in 3D, but I have. So if we rotated the curve about the x-axis, we can graph the resulting shape using the amazing GeoGebra 3D calculator by representing the curve as the radius of a circle. So this link right here illustrates this concept. So geogebra.org right here. So any cross section parallel to YZ plane has equation y squared plus z squared equals to f of x squared. In other words, this is just the equation of a circle, where this is r. Yeah, so that's r, and then you're squaring it. So this is just r squared. So if you have this here, and if this is the y, and I believe, yeah, this is the z. So that's y, this is z, this is x, and then x is then you'll have the radius is a variable function f of x. So radius is a variable function. As you move, as x changes, you're going to change, and then you're going to draw a different circle, and so on. So you get a 3D shape. So what you can do is in GeoGebra solve for z. So you'll have z equals 2 plus or minus square root. Now let's do this, plus or minus square root of f of x squared minus y squared. So move this over and square root it, and then you'll get this plus or minus, and then those correspond to the top and bottom of the curve. So the top and bottom, and here I've graphed it out. So solving for z, we get 2 square roots, which corresponds which correspond to a 3D surface. Yeah, so we have here GeoGebra. Here's a link right here, and here's our f of x. So you could write f of x equals to e to the power of negative x over 10 times sine x, and then you could plug this inside. Here's the first function, a of xy equals to square root the positive f of x squared minus y squared, and the next one is negative. So same thing but negative, and you get this bottom half, and then there's the top half and bottom half. And you graph it in 3D, it looks like this. It's just quite fascinating. If you click here, just open it up just to illustrate this calculator, which is quite amazing. And it's a bit slow because I'm using my Surface Pro as opposed to my PC, my computer or desktop. So it's a bit slow and lagging, but you can see it's pretty cool. And you can move it around, rotate, and play around with it. And absolutely fascinating stuff here. And yeah, so it looks like infinite string of beads, and you just keeps on going and on. Alright, I'll just leave here. So yes, that is the curve. And notice the zeros here. Well, the only place that can be 0 is the sine function. Sine function is the only way it can be 0. E to the negative x over 10. That only approaches 0 as x goes to infinity because of this negative power, but never actually equals it. The only time it equals 0 is when sine of x is equal to 0. So then, in other words, we can find the nth bead based on the zeros of the sine function. or the endpoints of each bead. So as we can see above, the solid looks like an infinite decreasing string of beads. Now let's determine the volume of the nth bead. So the x-intercepts of the curve occur where sine of x is equal to 0. Alright, so the x-intercepts of the curve when a sine of x equals 0, well, let's write that out. So we'll just draw it out. So here's the sine, and we're only dealing with x is greater than or equal to 0. So this is x, and this is our sine of x, the y, the vertical axis, the y-axis, sine of x, and this is like this. And it keeps going on and on. So this is pi, this is 2 pi, and let's make this a bit better. And it keeps going on and on. So that's 2 pi. Yeah, that's good enough. And then there's the 0 there. So it's 0 at, so I'll write this at sine, I'll just put this on here, sine of x equals to 0 at x is equal to n pi, which equals to 0, pi, 2 pi, etc. dot dot dot. So in other words, n is an integer right there. And I'll just put n equals integer, and in this case a positive integer because our x is our x is positive. Alright, so thus recalling the formula for disks we have, and we just go up to pi or n pi each time. So what we'll do is, and I'm gonna write this as so here is the x and y. We're gonna do this in 3D actually. So this is, I'm just gonna make this a straight line. This is our x, this is our y, and now we have our z, like this. So that's our z. I'm going to draw this like this, make it slightly decreasing, like that. So then at this point here, I'm going to call this n pi, and then the one behind it, I'm going to call this n minus 1 pi, so just the one before it. So it just generically wherever we are. So it could be at, yeah, this could be n, and then over there is n minus 1, and so on. So yes, that's where the beads are. So we're just going to look at it over here, and then now what we'll do is I'm going to take this shape and rotate it. So let's just pick a generic point here. Well, it's a generic point x here, and at this point we're going to, let's say, all the way up above here. Rotate that, and then it has a thickness. Or actually, instead of putting it over that side, I'm just going to grab this. So we're going to rotate this all the way across, like that, and then rotate across here, dot, 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 and then put this around here. Yeah, so we have this 3D shape like that, where this height is y, so all the way to the bottom, x, and this thickness is dx. So it's thickness dx, so in other words, the volume, so this volume right here, this full volume dv, we'll call this slice there, that disk, is equal to, well, we know that it's going to equal to pi r squared, y is r, so pi y squared times by dx, times by the thickness. So in other words, this is area equals pi r squared. This part right here. So that's just area equals pi r squared. And then dx is the thickness. So that's the slice of the volume. And yeah, and also just for completeness, I'm going to put over here, this at this segment here, this is at n plus 1 over pi. So yeah, at each 0, we're always going to be incrementing by 1, and then pi, like that. Alright, so that's dv, and now what we'll do is put in our nth one. So the the volume of the nth bead is equal to the summation, I mean not the summation, the integral. We're going to integrate from n minus 1 pi all the way to n pi of dv, of that slice. So we're going to go from here all the way to here. And then this equals to integral from n minus 1 pi, like this, n pi, and right over here, pi, then y. Well, we know y is our function. So y is our function over here, e to the negative 10 over x times sine x. So that's our y function. So we'll put it over here and write this down. So e to the negative x over 10 times by sine, e to the negative x over 10 times by sine of x, all squared, dx. Yeah, now dx is over there, so we just plug that inside, and now we're going to do some, well, slight simplification. This equals to, take the pi out, this equals to integral from n pi, and then from negative 1, n minus 1 pi, up to n pi. And now this is going to be e to the negative x over 5. Yeah, that's because of this 2. So when you have this x to the 2, then divide by 10 is 5. So x to the e to the negative x 5 over 5. And then times it by sine squared x. X all dx, like that. Let's put this neater. Alright, so that is our Vn. I'm going to put this Vn equals 2 and box this whole thing. Alright, so now that we have this formula right here, well, it's still just an integral. We want to solve it and solve the integral. So again, we were asked to use, the hint was use table of integrals or a computer algebra system. So we want the exact volume of it. So we'll just use a computer algebra system on line 1. So we can now use the computer algebra system from integral-calculator.com. So going over here, we'll have, and then you plug that inside. So integral from negative 1 minus n minus 1 pi times n pi of pi times e to the negative x over 5 sine squared x dx. And then you get this giant one here, this plus c. Yeah, this is just the indefinite integral or antiderivative. And now if you want the definite ones with the plug-in in this n minus 1 pi into and this n pi, we get this right here. So we get this right here, and then plug this inside and subtract it from the bottom one. We get this whole setup, and then this simplifies it down into this giant one. But we can simplify the resulting formula even more, because note that there's a sine 2 pi n. And in our case, for integers, this equals to 0. And this one right here, this equals to 1. And we could see that. So we can simplify the resulting formula. Again, recall, we always draw our cosine. And our cosine, I'll just put this theta like this. So recall right here, our cosine and sine. So I'm going to put this like this. This is cosine is at 1. And this is at 0 value. This is at over here is pi over 2, but then right here is pi. But the only one we care about is the 2 pi's, because we have this cos 2 pi n there. So this is the 2 pi there. This is 0, and this is cosine theta. So notice how this one goes all the way across to the 1. And it keeps going on. And likewise the sine, so sine's going to go here. If it's there, it's here. And then this negative is going to be over here. And then it goes to 0 here. So just the opposite of that. So this one goes to there, goes to here, goes here. So if it's a max cos, it's minimum. It's at 0, 0, 10. I mean sine, so sine theta. And that's 0 and 2 pi. So in other words, what we have is cosine of 2 pi n, where n is integer, this equals to 1. So all the 2 pi's, 4 pi, 6 pi's, all equal to 1 for cosine. And it equals to sine, for sine 2 pi n, this just equals to 0 for integers. So those are all, because remember we're dealing with integers, and so then this can go vanish, this can go to 1. And let's write this out. So, alright, so thus, let's put this all together. So thus our volume Vn at the nth bead, which is this is what we're solving for. Because remember, that's our Vn equals this giant integral, which equals to this, and it's simplified. So write 5 pi. So write this out, 5 pi over e to the 5 pi minus 1. E to the 5 pi minus 1. pi over 5 minus 1, like that. So that's this part right here, times by e to the negative pi, then there's an n over 5, and now times it by, and then this is all divided by first 202. 202, so that's all divided by 202, and let's go here. So this part right here, times by 10 sine 2 pi, that just goes to 0. So times it by 0, and then this becomes minus cosine 2 pi n, that's just 1, minus 1. And then this is plus 101. Plus 101, like that. So then this becomes 100. Yeah, it's 100, and this is a negative sign to the power of. So this is 100, and then 100 times 5 is equal to 500. So this is 500 pi over 202. And then this part right here, we can multiply this inside, and that becomes, this is times it by e to the pi 5, and this is, this could be, this is pi 5, this is pi over 5. So what we could do is factor out this negative pi over 5 out of there, so we go negative pi over 5, and then that makes it, when you take it out, this becomes n, positive n, and this becomes negative 1. Like that, and minus, and there's a minus 1 here, so e to the negative pi 5n, like that. And as you could see, this is a telescoping sum right here. Well, yeah, there's a telescoping sum when we sum it to infinity, when we take the series. So this is Vn. So here's the exact one right there. So 500, actually, well, we could simplify it even further. This 500 divided by 202 divided by 2 on each side. This becomes 250, so I'll remove this. This becomes 250 pi over 101 times it by e to the negative pi over 5 and minus 1 minus e to the negative pi over 5 n and Vn, like that. Let's put Vn here. Vn equals to this, like that. Alright, so we got the solution to part A. So let's go back to the question and look at solution part B. Or look at the question of part B. So that was the nth, that's the exact volume of the nth bead. So now we're asked to find the total volume of the beads. Alright, and also here, because this is just the integral, not the exact, we solve it, I'll just box this out, not the n there. I'll remove this. Yeah, just so, it doesn't, we're not emphasizing it as much. So now we got to find the total, so now we got to find the total volume of the beads. So in other words, take the sum to infinity. Again, that's because this function, the function we're looking at is going towards, it's just for x is greater than or equal to 0. So we're going to sum this up all the way to infinity. So this means, so that's the nth bead is this. So we're going to have infinite beads. Alright, so let's take a look at the solution to B and find the total volume. So method 1 is a telescoping sum, as per always. Alright, so the total volume is, using none other than the telescoping sum, is, so this is the nth one, but I'll just write it all out from the integral part. So this is the integral of the nth bead, but we're just going to go from integral from 0 to infinity. So we're going to go from the beginning all the way to the end, and then just write it over here. So the total volume is V equals to pi, take pi out of there, 0 to infinity of e to the negative x over 5. Yeah, so e to the negative x over 5, then times it by sine squared of x and all dx. And let's just double check that here. So yes, that is right here. So e to, from 0 to infinity of pi e to the negative x over 5 sine squared x dx. So this equals to, the summation, the summation of the nth bead from n equals 1 all the way to infinity. So we get infinite number of beads. So Vn and that is our top part right here. Just put this all together. Yeah, then this will be summation up to infinity, n equals 1 of 250 pi 101 times, and then e to the negative pi over 5 times n minus 1 minus e to the negative pi over 5 times n. Alright, so this equals 2, and let's just write this out again as it be the telescoping sum. Take the 250 out. 250 pi over 101. This can be times by the limit as n approaches infinity of the nth partial sum, which is, we'll just plug in this inside. Yeah, for n equals 1, we'll have 1 minus 1 is 0, so we'll have e to the negative pi over 5, times 0. Let's put this like this, times it by 0, minus e to the negative pi over 5 times 1. So that's this one right here. Again, we're going to get the telescoping sum in a bit. So next one is put n is equal to 2, and we're going to put bracket e to the negative pi over 5. 2 minus 1 is, well, just 1. And then minus e to the negative pi over 5, and then then this is just 2. And notice what we have here. This is right here. This cancels with this. That's just e to the negative pi over 5 times 1, and so on. And then the next one, let's go n is 3. We'll get plus e to the n minus 1 is going to be 2. It's pi to 5, and then times by 2. Minus e to the negative pi over 5 times by 3. And then this cancels with this, and obviously dot 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 all the way to the nth one. We get e to the pi over 5 n minus 1 minus e to the negative pi over 5 times it by n. And then I'll close bracket, and then again this will eventually cancel with this using the telescoping sum, and we're left with just this and this. So this equals 250 pi times by, or divided by 101 times it by limit as n approaches infinity of e to the negative pi over 5, and this is just 1, e to the 0, that just becomes 1, minus, and then it's just a minus right here, e to the pi over 5n. And instead of writing it like this, because there's a negative exponent there, I'm just going to put it at the bottom. So e to the, and make it positive. So e to the positive pi, so 1 divided by e to the negative, e to the positive pi over 5 times by n, like that. And then notice that this part right here, what we get is a 1 over e to the infinity as n approaches infinity, which is again 1 over infinity goes to 0. So in other words, this equals to 250 pi over 101 times by 1 minus 0. Yeah, so in other words, the total volume approaches 250 pi over 101. So it's equal to 101, like that. Alright, so that is the volume, but that was the method 1 using telescoping sum, but we could also use another method, so solution to B, method 2 using the geometric series. So if we start off by using the volume in part A at the start of our simplification, we can notice a geometric series. Yeah, going all the way up over to here. So starting from here, if we just start from here, and so there's 100 right here, multiply that by 5, get 500 over here, and so but simplify it to 250 pi over 101. So we'll start off at this position here, and then notice we can get a geometric series out of it. So let's just write that whole thing out. Actually, I'm gonna write the summation from infinity, starting from 1 of 250 over 101, and then we're gonna have pi times it by, and then if you recalled how that looked, it's key to make sure everything is correct. So e to the pi divided by 5, minus 1 times it by e to the negative pi n over 5, and then we'll have this 250 pi over 1. So this is pi positive pi over 5 minus 1 times it by e to the negative pi over 5 n. And now compare that with a geometric series, which is the summation, and we're starting from n equals 1. So we're going to write it down as this. So if we recall geometric series, infinity, n equals 1, and it's a r n minus 1 equals 2, and then this equals 2. When you plug in 1, you get, well, a. So a, and then r 1 minus 1 is 0, then plus ar plus ar squared plus ar cubed plus dot dot. So that's key. Dot dot. Alright, so we're starting from n equals 1 on the top one as well. So what we can do is, well, first of all, note here, or I'll put this arrow like this. E to the negative pi over 5 n is equal to, what's equal to is, well, I'll just put a pi over 5, so n minus 1 plus 1, so that we can get the n minus 1 set up. This equals 2 e to the negative pi over 5 times it by n minus 1, and then plus 1, and it's going to be a separate over here, plus, but then there's a minus sign out there when we multiply that inside, pi over 5, minus pi over 5, like that. And this just equals 2 e to the negative pi over 5 n minus 1 times it by e to the negative pi over 5. So in other words, we can multiply this inside this that bracket right there, and then what we're gonna get is the summation up to infinity from n equals 1 of 250 pi over 101 times it by, and multiply that inside. So e to the negative pi times e to the pi over 5. So there's pi over 5. Those just add up and those go to 0. They cancel. So we're just left with 1. And then minus e to the negative pi over 5. Like that. And then times it by e to the negative pi over 5 and minus 1. Like that. Yeah, so in other words, what we have is this is our a. So that's our a. And then this is our r, e to the negative pi over 5. And that is our r. I'll just put this arrow here. And that's our r. And so note our r equals to, our r equals to e to the negative pi over 5. And then this is the same thing as writing e to the pi over 5. And this is less than 1, because this e number is bigger than 1. So then this means that, this is going to be converges. So the geometric series converges. And so this is less than 1. And again, note here, I'll just put a note, or recall. I'll just put a note. Note e to the x is greater than 1 for x is greater than 0, because if you recall the graph for e to the x, if this is x, this is y, or e to the x. Let's put this as y, and this is at 1. E to the 0 is 1, and as the number as you go negative, you're going to be that's going to be dividing by a large number that goes downwards there, and this goes up like that. This is y equals e to the x, and it's exponential curve like that. So this is greater than it there. So note it's so put that here. So hence 1 divided by a number greater than 1 is going to be less than 1. So thus, go over here. So thus, the volume V is just going to be equal to, as a geometric series, just a over 1 minus r. And then a, we know, is equal to, a is equal to 250 pi over 101. So this whole thing, then times by 1 minus e to the negative pi. 1 minus e to the negative pi over 5 divided by, and then yes, divide this all by 1 minus r. And r is also equal e to the negative pi over 5. And this is going to be e to the negative pi over 5. So in other words, the top and bottom cancel. Yeah, so then this whole thing cancels with this. So we're just left with equals 250 250 pi over 101, exactly as our first solution. So yes, that's pretty fascinating stuff.